In this video, we're going to be simplifying roots and powers, roots of all kinds and powers of all kinds, and see now we can undo all those operations the easiest. So let's just get going. We got to know our exponent properties, so make sure you review those before watching this video. Right off the bat, we'll start with a square root. Remember, a square root has an invisible index. It's just implied that it's a 2. Let's say that we were taking the square root of 49 times x to the third. So what we want is we want to take out perfect squares or pairs of multiples, right? Since we're dealing with a square root, we want pairs. So if I factor all this down, maybe you know that 49 is a perfect square. If not, it does not matter. If we factor it all the way down to our prime factors here, then it will help us visualize what's coming out of this radical. So here I have a pair of 7s. So I circle it, I cross them both off, but I take out one of them and I write it on the front. So the square root of 49 is only 7, right? So we don't take out 2 7s, we only take out one of them. We do the same thing with all our other pairs. Circle your pairs, cross them both off, and take one out. So we don't have another pair of x here, so that stays under the radical. We can't take the square root of just x, but we did take the square root of 49 and x squared. The square root of x squared is just x. So that's square roots, and that's different than other roots. If we have a cube root, we're going to be looking for triplets. If we have a fourth root, we're going to be looking for quadruplets. You're always just taking out those groups that match with your index number. All right, let's try another example here. Let's do the fourth root of x to the third, y to the fifth, and z to the eighth. So again, we're looking for fourth roots. That means we're looking for quadruplets to gather and take out of our radical here. So if I factor it all the way down to the prime factors, it will help visualize. We got 3 x's, we have 5 y's, and a bunch of z's, 8 z's. So I'll write that down here. 4, 6, and 8 z's there. So we're taking out quadruplets because we're taking the fourth root. So none of our x's are going to come out because we don't have 4 of them. We can't take the fourth root of a cube, but we can take 4 of our y's out. So cross those off. We write 1 on the outside. That means there's still going to be another y left over. How many z's can we take out? How many quadruplets do we have? We got 1 quadruplet there, so we cross all 4 of those out and only write 1 on the outside. And we got another 4. Cross those off, take out another one. Well, if we have another z, we're multiplying everything on the front here, so we really get y z squared on the front. And I have to rewrite anything I left over under the radical. I had 3 x's being multiplied, that's x to the third, and I had 1 y left over. So this here is my final answer. We could also think about changing the form. Instead of it being radical form, we could write it in exponent form. That actually might help you. Maybe you prefer it that way. So we got x to the third, y to the fifth, z to the eighth, all to the 1/4 power. So if I distribute my exponent, I'm multiplying my exponents, right? So I get x to the 3/4, I get y to the 5/4, and I get z to the 8/4. So if I can simplify any of this, I can simplify some of it here. Can't simplify my x's. Still got x to the 3/4. Let me get rid of this stuff here on the right. Let's rewrite our answer. See what we get here. Oops. Alright, so x to the 3/4, that stays, right? And can't do anything with that. This y to the 5/4, though, becomes y to the 1 and 1/4, right? So we got a 1 that comes out. And we still have a 1/4 inside, right? All right, let's look at our z's. We get z squared, right? So that all simplified. We got two z's coming out. Z squared comes out. And what's left over are our fourth roots of things. We had x to the 3rd and a y. That matches with what was left over up here. So again, changing the form may help you simplify. Depends on which form you like better. Alright, let's try another example here. Let's try an example in exponent form. Let's try 27x to the 1/3 power. We could change the form. Maybe that'll help. 1/3 power means we're taking the cube root of something. We're taking the cube root of 27x. So now factor that all the way down. Maybe you know that 27 is a perfect cube, in which case we could just take the cube root of 27 out. But maybe you don't. So let's figure out how to get it if we don't know that. Factor 27 down all the way to its prime factors. We got 3 times 3 times 3. That gives us 27. And we got that x there still. So we're looking for cube roots. That means we're looking for triplets. Well, here's a triplet right here. Cross them all off and write 1 on the outside. And we don't have 3 x's being multiplied. We can't take the cube root of just x, so we gotta leave it. And this is our final answer, 3 times the cube root of x. Let's try another one here. Let's try a negative exponent. What happens here? This would be the square root, right, of x to the -7th. So think back to what a negative exponent means. It doesn't mean multiply by a negative number, it means the inverse. So we want to flip it, put it under 1. So we still have the square root of x, and it's still to the same power, but now it's under 1, right? That's what a negative exponent means. And now we're about to get to where we're going in our next video here, which is how to rationalize roots of any power, right? Or any kind. If I want to rationalize, I need to multiply top and bottom by basically whatever the denominator is. That's the most basic way of doing it. But sometimes multiplying by whatever the denominator is will give you a fairly large number, and then it's quite difficult after that to simplify. So if we rationalize by the smallest number possible that we can still do and still get rid of that radical, it helps a bunch. So we'll get into that in the next video. Otherwise, keep practicing simplifying any roots and any exponents.